what we've done is we've invited Dr. Carolin Villforth to come along and tell us all about supermassive black holes and how to feed them and what happens when you do. So you're a senior lecturer, I understand, at the University of Bath, but you got your first degree in Heidelberg in Germany, and then you sort of touring all over. I think you got your PhD in Finland.
Yeah, in Turku.
Yeah, and then you went on a world trip. Now, I can normally remember stuff, but this is such a cool world trip. So, research positions at the Nordic Optical Telescope on the Palma in Spain, the Space Telescope Science Institute in Baltimore, USA, University of Florida, and University of St. Andrews as well. And you've managed to get to Bath as well.
You did, I did.
So I'm delighted to welcome you. We're just going to do a bit of swapping over and making you sort of the controller, and then I'll hand over to you fully. Feel free to talk to each other whilst
Yeah,
we're
if
doing
you go to the Palma, so I work at a telescope there. If you want to do like observing next to the Nordic Optical Telescope is where you go, and best seeing on the mountain, which is advertising my old employer.
No, I do know somebody who went there with his family. We did tell his family he was taking his telescope with him.
Yeah.
They thought they were going to the beaches. He was going for that.
For that, and it's really high up, and the air is really thin, and you can't do anything anymore because the air is so thin. But great seeing, so it's all worth it, really. Am I in charge of the screen now?
Yeah, you should be. That's you, yeah.
There I am.
Okay.
Right, well, thank you for inviting me. Should I stand about here? Where should I stand?
You can stand right, just in front of those posters would be great.
Okay, so that there. Right, so as Simon already said, my name is Carolin Villforth. I work at the University of Bath, and I will try to explain to you about supermassive black holes, how to feed them, and what happens when you do. And as I learned, Becky Smethurst was here, so basically you should have already know all of my names. Actually, I haven't forgotten anything. Right. Should I get started, or is there anything else?
That's it, go for it.
That's it. Okay, right. Then I get started. So I always start these talks with the general thing of saying, well, when we all, as humanity, started doing astronomy, I guess we started looking up at the night sky and seeing hopefully something like this. So this is what all humans can see with their own eyes, and it's of course the Milky Way, and you all know this. And of course, if we look up, basically what we see there in the Milky Way is basically stars. So every point here, apart from a few galaxies, and here is basically a star. So basically, the night sky is filled with stars. So this would be a close-up picture of something like the sun. And now I'm telling you really things you all already know, but I'll get there. And these stars might have masses between the mass of the sun and something like 100 times the mass of the sun. For me, that's very light, and I'll tell you later what heavy is. And these stars together form something like galaxies. This is a galaxy. You all might know which galaxy. I don't know which galaxy. It's a pretty galaxy. And this is a spiral galaxy. So these stars will form these spiral galaxies. What you see within there is the spiral arms. You see the dust lanes, and you see the color gradients, which also show you different stellar populations. So the stars, of course, form galaxies. Galaxies don't exist in isolation. So galaxies like this will interact with other galaxies. And when they do, we get something like this here. So basically what you see here is an interacting galaxy system. You see two spiral galaxies like they were before, but they are now interacting. So you see the disturbances in the system. You see these kind of disrupted spiral arms. These don't look like normal spiral galaxies. And you see what we call the tidal tails here in bridges. So basically that's gas connecting between the two galaxies. So what's going on here is those two galaxies are colliding, and that's going to be a very, very violent process. I'll show you some simulations of this later on. And once that is completed, most of the gas and stars, gas will be used up in star formation, and we get to the galaxies that are less appealing to everyone, which is elliptical galaxies. So this is, of course, a galaxy a lot less pretty than the one we've seen before. And the difference we have here in this galaxy is we have far less gas. We're not really forming stars. It looks kind of boring, but it is a galaxy. And until the 1960s, 1970s or so, this is what astronomers knew about the night sky, right? This is what's up there. We can talk about the details of, planetary nebulae and supernova and so on, but basically there were stars, they form galaxies, there's some dust in them, that's what's out there. We need to study that, but that's what's out in the world. And what I'm going to tell you about today is basically a new addition to this picture, and that's supermassive black holes. But where do we find these supermassive black holes? So what I'm going to tell you once I press play is this is going to start a movie that's somewhat dizzying because it's going to start to zoom into the Milky Way. So what we have here, as before, is the Milky Way. And this film is going to start to zoom into the center of the Milky Way and start to reveal the supermassive black hole. So let's get started. So what we're seeing here is the immense amount of detail that we have within the Milky Way. That is a lot more choppy than it is on my screen, but we just have to live with that. So we're basically zooming in, and you see all this massive amount of detail that is revealed here. So all of these are stars. You see all this massive amount of detail, and we're finally zooming into the very, very center of the Milky Way. And as we're zooming in here, we're seeing the stars move, right? We're seeing the stars, and this film shows a time frame of 10, 20 years or so. We're seeing these stars orbit. And this movie will now show you the orbits. So we're seeing the stars orbit a very, very central point, which we call Sagittarius A star. And what we as astronomers can do is we can take these orbits, we can apply Kepler's law, and we can basically figure out what the mass of the thing is in the center. The same way we could measure the mass of the sun from the orbits of the planets. Simple as that. We can basically measure the mass of the thing in the center. The thing in the center has about 4 million solar masses. There are 4 million solar masses. That's a lot, right? That's a lot. If that were matter like stars, we should see that, right? We should see something. We should see some emission. But in fact, the very center that is being orbited here, there's nothing there. There's no light being emitted at all. And what that tells us is that this appeared very conveniently. What we have in the center is basically a black hole. I didn't actually time this, but basically, what this is a black hole. That's the only explanation we have for this, right? And you can see the scales here. This is 2 light years. This is tiny. Well, this is a tiny, tiny region. Okay, so this is exciting. What this tells us is that in the center of the Milky Way, there's a new kind of object, the kind of object we hadn't known about before, and that is a supermassive black hole, right? And this film continues, and I stop it now. I should remind people that this discovery got the Nobel Prize in 2020. So from the observational side, that was Andrea Ghez and Reinhard Genzel. Both of those groups did those observations I just showed you, incredibly, incredibly difficult to do. And Roger Penrose for the theoretical side. So that is specifically for the Milky Way, black hole. Right. So this is exciting. Supermassive black hole, they are a new addition. Now we can ask ourselves some questions, which is basically, so we have all these galaxies here, and what we learned later on is basically every single of these galaxies has a supermassive black hole in the center. The Milky Way is not special. So one of the things we can ask is, well, how massive are they? Right, we know it for the Milky Way. I told you about 4 million solar masses or so. That's okay. How much are they overall? So basically what we know is the majority of the mass, even though that 1 million or billion solar masses is a lot, the majority of the mass in the galaxy, even ignoring dark matter, is still in gas and stars, so baryonic matter. The black holes themselves have masses that range from millions to billions solar masses, so that's quite a lot. And another thing we learned as astronomers is that irrespective of how big the galaxies is, the black hole is always about 0.1% or so of the mass that is in stars. So it has always about the same contribution, right? But contribution is kind of pathetic. I mean, that's a lot, but you know, overall, this doesn't really matter. Yeah, so this is a complicated plot. I'll try to show this and then explain it later. And if you phase out now, just ignore it and I'll return to the pictures, right? So what I'm showing here is another argument, basically, why we should care about supermassive black hole. So this is a super cool plot. So what this plot shows, I will return to the pictures, is the black hole mass here, and that is some measure of the mass of the galaxy. So that is what I just showed you, is basically we have a strong correlation between those two that shows you that basically as the galaxy gets bigger, the black hole gets bigger. So this is the argument I made, that always about the same percentage of the mass is in the black hole. And this is a very exciting finding, right? So keep this in mind, always about the same amount in the black hole. And I'll come back to it after I explain something to you, which is, so what I'll try to explain to you today is basically, I'll try to answer the question, does the black hole matter? So as I said to you, the black hole has a high mass, but it's kind of tiny in the overall scale. So basically, does it matter? And by does it matter, what I mean is, does it change the outcome for the galaxy? So what I show you here is this lovely picture board of different galaxies. So basically, if I took the black hole out of this galaxy, would it look different? Does it matter for the galaxy as a whole? Does it make a difference? And I will try to convince you by the end of this talk that it really, really does. Right. Okay, we return. So what we're going to say, does the black hole matter? The first question we could ask, well, gravity, right? This black hole is so massive, millions to billions of masses. The gravitational impact of it must be massive, right? Well, we can think about it in more detail. We can say that, well, so the black hole mass is millions to billions solar masses. The black hole size is very, very small, smaller than a light year, so it's tiny. And we know that still the majority of the mass is in stars, gas, and dark matter. And the other thing we know is a galaxy overall is huge, like tens of thousands of light years. So does the black hole matter for the gravity? Well, it turns out it doesn't. So basically, if you think about being a star within this galaxy, basically one of the questions is, can you feel the black hole? And it turns out you can't, because basically there's so much mass all around that if you remove the black hole, it basically doesn't make a difference, right? The only place it makes a difference is in the very, very center. So in the very, very center, the black hole is close enough to have a significant impact. But for most of the galaxy, if you took the black hole out, it wouldn't matter because there's so much mass around. So at some point, I tried to draw the circle of how big this region is onto this, and I can't because it won't let me make it so small. So I could tell you that I drew this circle on. It's not true, but you know, you can see it anyway. Right? So basically, what that means is that in terms of gravity, the black hole doesn't matter because the overall mass of the galaxy dominates. So that's disappointing, I guess. So basically, does the black hole matter for the gravity? No. So unless you're in the very, very center, so that we're talking like tens to hundreds of light years, and that depends on the properties of the galaxy, doesn't matter at all. No impact whatsoever. Okay, but I told you that black hole would matter. So how? And the surprising answer to this, given that it's called a black hole, is that what matters is the emission from accretion onto the black hole. So we think of black holes, given also their name, as objects that swallow up all light. And that's true, right? So that's the event horizon. Basically, if light gets near that, everything is swallowed, even light. So we think about it, oh my God, black holes are really dark, like no emission comes out. And that is true. But the one thing that is also true is that if we throw gas onto the black hole, that's an entirely different matter. So what we see here is an artist's impression, not a picture, of accretion onto a supermassive black hole. So what we can have is basically if we throw gas onto the black hole, it will basically form an accretion disk. So there will be, so it will start basically circling inward. And as it does that, it kind of heats up to very high temperatures. And that is what's emitting radiation, right? So black hole itself doesn't emit, but if you throw gas onto it, you get a lot of emission. So basically, if we feed the black hole, we get emission from accretion onto the black hole. But now you might think that, well, but the black hole mass was so tiny, how could this possibly matter? There's so many stars. And now we have a diagram because, you know, so if this seems scary to you with the axis and all, I'll try to explain it. So basically what I'll try to explain to you now is like why accretion to the black hole actually emits a lot of light. Because we think generally of stars as being very efficient at creating light. We'd like to have fusion on Earth after all. So how does a black hole create light at all? So what I've drawn here is, this is a supermassive black hole, or any black hole. And then basically along this axis, basically along this line, you go further and further from the black hole. And what we have here is the potential energy of mass orbiting the black hole. So we know that energy needs to be conserved. So if matter is orbiting here, it has a certain energy. And if it wants to fall in, it basically has to follow this line. This means it's losing the potential energy. So what that means is that the energy needs to go somewhere, right? If I fall into the black hole, I'm basically losing potential energy. So all this energy I'm losing, because I can't break physics, physics has to go somewhere. Now, where does that go? Where it goes into is that as gas is falling into the black hole, slowly kind of falling towards it, it basically interacts with other gas around it. It starts to heat the surrounding material to these high temperatures and starts to emit. So basically, accretion onto the black hole, if you have this very dense disk, basically through the interaction with the material, you're turning the gravitational potential energy into radiation. So the energy comes out. This is how the black hole makes light, gravitational potential energy to radiation. So why is the black hole so great at this? Basically, if I take this step here, you basically say, well, the distance here is quite small, right? So I'm not losing a lot of energy. Whereas if I'm here, I'm losing a lot of energy as radiation. So basically, the closer I get to the black hole, the better it gets at kind of releasing energy as radiation. So that's nice. But then you might say, well, but stars, black holes, they are the same, like gravity works for everything. The reason a black hole works so well is because it's so small. So if I had a star, I basically don't have access to this part of the gravitational potential. So this is why black holes are so fantastic at creating radiation. So this special process we have for extracting energy is basically the answer to the question is like, does the black hole matter for the galaxy? In terms of emission, it surprisingly really does. And the reason for that is that the efficiency that stars have at creating radiation is very low. We'd still love to have that on Earth, right? That's fantastic. But compared to the black hole, it is nothing. So for the black hole, about 10% basically of the rest mass get transformed into radiation. It is absolutely amazing, right? There's nothing like it. So that means that surprisingly enough, the black hole, despite its name, actually has an impact only through emission onto the galaxy. That's why it matters. And that is why I can ask you, what do you think that is? Does anyone know this object, or what kind of object do you think that is?
A quasar?
It is a quasar, yeah. If you hadn't known what I'm talking about today, you might have seen that more as a star, right? It looks quite pointless. So this is a quasar. This is 3C273, basically the first quasar. And basically what this shows you is what I just explained to you about this extreme emission from accretion onto the black hole. So what we have here is an accreting black hole. And this outshines the entire galaxy. I think it's about 100 times brighter than the galaxy it's in. So still, we have the mass of the black hole is tiny, tiny. But if you're feeding it the right way, it outshines the entire galaxy. So this is why quasars look like that, because black hole accretion is so efficient. And if we look out into the world, basically, only about 1% of galaxies have an actively accreting black hole. So most of them, the black hole, like the Milky Way black hole, is kind of boringly just sitting there. In about 1% of cases, it's accreting. And then you see these kind of extreme emission. And these are the objects I like. I don't like the other galaxies. Right. So quickly going back to this plot. So this gets very sciencey, and then I return to the pictures. So if we come back to this plot, this is actually a really, really weird plot. It's a fundamentally weird plot. Because what that tells me is that the mass of the black hole and the mass of the galaxy is really tightly correlated. So they're very strongly connected. But I just also told you that for most of the galaxy cannot feel the black hole, right? It cannot feel the gravitational impact. So one of the questions is, basically, how does the galaxy then know to have the right mass in the black hole, right? This is really, really weird, and this is fundamentally a weird plot. So coming back to this, what this plot kind of tells us is that, well, the gravity can't do this, right? Because they cannot communicate with gravity, so the galaxy doesn't know what mass the black hole is. So what that tells us is there must be some way for the black hole to communicate with its galaxy, to basically tell it the mass it currently is and what mass it should be. So there basically should be a causal connection between those two, right? So this plot, incredibly weird, really, really weird. So what I'm going to try to talk to you about for the rest of this talk here is thinking about, since black holes do have these extreme phases where they're emitting a lot of light, because first of all, how do we get them to do that? Like, how do we feed the black hole? And then the other question to ask is, well, what does that emission do to the galaxy? So if I'm getting all the energy out, what does that do to the galaxy? And could it potentially tell me why this is happening? Basically, because that energy emission could be a way for the black hole to influence the galaxy. So let's start simply. How do we feed the black hole? So going back to this example galaxy, it's very, very pretty. We can think about the following. So as I said, the black hole basically sits here at the center. Most of the galaxy is rotating. It's stable the same way that the solar system is stable, and we're all not just falling into the sun. So if I want to feed the black hole, what I would have to do, right, is feed it some gas. So basically what I want to do is transfer some gas towards the center of the galaxy. But as I said, that most galaxies are stable. They're stably rotating. The other thing we can think about is like, how much mass does the black hole need to be active? And the answer to that is, for some of the bright quasar, it needs something like 1 solar mass per year, or up to 10 solar masses per year. So that's basically 10 suns a year or so, and then it will be active for 1 million or 1 billion years or so. So it needs a lot of material, right? It's very hungry, it needs a lot of material. So that basically means that if I'm in a galaxy like this, to get mass to the center, in many cases, that is very, very difficult to do, because the galaxy is stable, and again, I need to move a lot of material. So what do I do then? This galaxy is stable. Not much is going to happen. Maybe a bit of gas is going to trickle in. Well, one way we could solve that problem is something we saw before. We just smashed some galaxies together. This is a simulation rather than a movie, as you might guess. Can I do? So what you're going to see, so what you see here, so this is the scale, this is 10 kiloparsec, so about the size of the galaxy approximately, more or less. And then you might want to watch up here, there is a timer here. This starts at 0 gigayears, and then we'll count upwards about 2 or 3. And what you see here is 2 disk-like galaxies coming in. So what this is showing is like what happens to galaxies when they collide. Okay, they start. I think they start. Yeah, they are. Here they are. So galaxies are coming in, and at this point, those galaxies are rotating quite stably. And now you see the first passage of this galaxy. You see something you saw in the pictures before, which is you start to see these disturbances here. They start to look more asymmetric. You see the tidal tails coming out. So those galaxies, for now, they're looking okay, but they have some disturbances to them. And now this is going to go a lot worse. And now, as we basically kind of approach what we call second passage or so, you see the system is a lot more disturbed. You see a lot of materials being flung out very far, and at the same time, the center of the galaxy is contracting. And it keeps going like this. Yes, 2.7 gigayears, took quite a while. So what we've seen here is basically how mergers of galaxies can affect galaxies. And the way they affect galaxies is they take a stable galaxy and they basically disrupt a lot of the orbits, right? This galaxy is no longer stable. And you saw as this was going on, you see some of the material flung out, which means other material must come closer in, basically conserve angular momentum. So that's kind of, if you have the figure skaters that spin and put their arms in, and that's kind of the same system, right? We have some of the material has to come in. No, that's actually a bad analogy. Forget about it. Sorry, because that's something else. Anyway, right. So what this shows you is that if you have a merger of galaxies, any kind of disruptions, that's something that would feed the black hole because you're driving gas inwards, and you get very high densities in the center. So one way to feed a black hole then would be to collide some galaxies, or to disrupt the galaxies in some other way. Now you might be terrified by this since you're amateur astronomers. So a lot of things I've and I copied this from a Sheffield seminar and then I forgot to remove it. So sorry about that. So one of the things I've done through a lot of my career is basically look at exactly this question. So I've looked at accreting black holes, non-accreting black holes, and I tried to find signatures of disturbances in the galaxy. So this is an example from some science papers here, where we see beautiful, wonderful pictures of galaxies that we can study. And basically what we do as astronomers is we look at these pictures of galaxies here. We get rid of this annoying quasar, this kind of bright emission from the black hole, and then we look for disturbances. So here you see some disturbance, and here you see some disturbance. And this is actually a big field of research. It's actually really, really complex if you get to the details. And what all of this has taught us is that if you smash galaxies together, you get more black hole accretion. It is not the only way to get black hole accretion, but we can see signatures of that. So we know that if you disrupt galaxies, you can make black holes accrete. We don't yet know all the answers, but we kind of know that that's one of the contributions we have to black hole accretion. And that is simply because generally galaxies are stable and gas doesn't want to fall inwards. So that is somewhat the first question, right? So that is kind of so the answer to the first question is like, how do you feed black holes? Generally, we have to kind of disrupt the galaxy a bit to get enough gas inwards. But if we could do that, we can have some black hole accretion. And we can go back to a picture of this galaxy. So I showed you this before. So this is an accreting supermassive black hole. You see action spikes in the center, so there's a bright, relatively bright quasar here. This is a Markarian 231. Is that in the south and the north? Is it visible from here? maybe not. Since you don't know it, it's great, it's a lovely galaxy. So you see that this is an accreting supermassive black hole, and you see in this one, for example, you see signs of this disturbance, right? This looks a bit messed up. It's asymmetric here, it's asymmetric here, it has this tail coming out. So that is one of these examples of this specific object. Great galaxy. Where we see black hole accretion and we see a recent disturbance. Okay, so now we know how to feed a black hole, at least kind of. We might not know all the answer. But then the question is like, once we have it accreting, what does it actually do? Basically, what effect does the radiation released from the accretion have on the galaxy? And to answer that question, we'll go a step backwards and think about what is there in a galaxy. So if we think about galaxies, we might generally think about pictures like this, where we have what I would call existing stars. So that's kind of the optical range. You have your existing stars. So in the center of the galaxy here, you see the slightly redder colors, that would be older stars, less star formation. And you see the outskirts here is a bit bluer, new stars. So basically that's a galaxy, that's stars that already exist. So there's stars in the galaxy. The other thing we have in the galaxy is, of course, gas and dust, right? We need the material to form new stars, and of course we have supernovae, outflows, like all stars, dead stars, all that stuff as well. So the other thing that we have in the galaxy is basically gas and dust. And this is a view here. So here basically have the optical, and over there you have an image from Herschel. So that's basically cold gas and dust. That's something that would form new stars, right? And the reason we want this gas and dust to be cold to form new stars, it basically needs to collapse. If you heat something up, it tends to expand. So we want it to be as cold as possible, so it's all nice and close together, so it can form new stars, right? And then we have X-rays. Just forget about the X-rays. So basically that means that we have a galaxy that has different components, stars and gas and dust that might form new stars. So the question we must ask then is like, what does the accreting black hole do to either of those? Is kind of the questions we should be asking. If it's going to have an effect, what does it have an effect on? So basically this is the same or similar picture here, is basically showing that we have a galaxy here with kind of the existing stars, these kind of dust lanes, and basically within that galaxy growth, so kind of new star formation happens through transforming cold gas and dust into new stars. New stars are being added here. And once we have a galaxy that contains little cold gas and dust, that will not form new stars. So this is the galaxy I showed in the beginning. This is an elliptical galaxy. What we have here is very smooth. We don't see these dust layers, so we don't have this new material that could make new stars. This one is basically done, right? It has the stars, it's done. And there's no new star formation in this galaxy. So now that we know that, we kind of know what's in a galaxy, we know how it makes new stars. We can again ask the question, what effect does the radiation released from the accretion have on the galaxy? So we can now go to a cartoon thing. We can basically say, well, so what we have is some kind of an accreting supermassive black hole in the center. That's this little gray thing here. We have the accretion onto it. That's emitting all the radiation. And what does that do? So the first thing to keep in mind is just because something is bright, it doesn't need to have an effect, right? If the light just goes out and escapes and to be seen by astronomers that, watch it keenly, it doesn't really do anything to the galaxy. You need to interact with the material in some way. If it doesn't interact, it's kind of pointless for the purpose of this exercise. So what we can ask is basically, what does the black hole do to the stars in the galaxy? So the stars that are already there, that are existing, does it affect them in any way? What does it do to kind of general gas clouds in the galaxy? So just the gas that's hanging around. And what specifically does it do to kind of very cold gas, so the one that's like just about to form new stars, the one that's just about collapsing? Okay, so what does the black hole do to stars in the galaxy? Nothing. At some point I should put a delay on it saying nothing. Right, so if we think about this, right, so what does the black hole do to stars in the galaxy? If there's a star in the galaxy, what it basically sees when there's an accreting black hole is like, well, it's really bright over there, right? There's a lot of emission. But say, if you basically would shine a lamp on the sun, it wouldn't really care, right? You're not adding like significant energy to it. It will be relatively far away. The stars are also kind of relatively small, so basically it doesn't have any effect at all, right? The stars are not really bothered by there being something very bright in the center of the galaxy. So for the stars, the black hole doesn't matter. So all your existing stellar populations, all your existing stars will basically stay as they are. They're fine, and nothing happens to them. So that's good to know, I guess, for ourselves. But if we move on to kind of other aspects, other things we can think about is like, well, what might happen to cold gas in the galaxy? Right, so for stars, I said, like, well, you know, they're already quite hot in a way, right? You put a bit more light on them, who cares? But if there's cold gas, we're talking about gas that's kind of a few Kelvin, so that is like near absolute minimum. It's incredibly cold. Well, in this case, it's a very different thing, because in this case, you're shining a bunch of light in it, right? So there's very cold material that might be about to collapse to form new stars, and now you're pumping energy into it. And you're pumping a lot of energy into it. So if you're exposing cold gas to all that light, what you might have is you'll start to heat up, right? You're just making it hotter, like a snowman on a sunny day or something like that, right? You're just shining light on it, you're making it warm, it will absorb it. So the cold gas in the galaxy is a completely different thing, because the radiation, so all this light from the black hole accretion, just start to heat it up. And so that would mean all this kind of the orange part here, all this material that's kind of ready to form new stars, might now be too hot to form new stars. So that's disappointing if you want to make new stars. So I guess I should have, so in this case, it really can have a massive impact simply by heating material and basically stopping star formation. So here it can have an impact. If we're thinking more generally, apart from just heating material up, the radiation might also have a different impact. And this one is kind of cool, and I'll show you some pictures for that later, is that if we think about things like solar sails. So the way solar sails work is basically the photons of the light hit it and basically transfer momentum, so you kind of just push it along a bit. If I held my hand up, you know, I wouldn't feel that from that light, it wouldn't be kind of knocked backwards. But if you have a very large sail and you basically expose it to a lot of light, it will start to push it a bit. It's not a massive effect. But if we think about this analogy where we have solar sails floating about, we also have gas clouds within the galaxy. So they might not even be so cold they're just about to form stars, and they will feel the same. So they will feel this radiation pressure. So they will basically just slowly be like kind of kicked about a bit. And if they get kicked about enough, they might just, you know, accelerate. So if we, yeah, oh no. That's the process. So basically, the stars don't care about the accreting supermassive black hole, but all the gas does. So that's both because it might be heated or it might be kind of pushed about. And this is an artist's impression. So what we can have then is, this is an artist's impression, but there's actually evidence for something like that. Is if we have the black hole in the center, we could have this kind of this gas just being pushed out of the galaxy. So there is enough energy, and this is kind of based on actual observations from the accretion, that all this basically pressure on the gas clouds and the fact that you're heating everything up and it wants to expand, we can really just push the material out. And we see that happening all the time. So the black hole can really have an effect on the galaxy. It can really have an effect on the galaxy because there's enough energy to make the gas hotter and to push it away. And so what we then have is basically the gas just streaming out. And once the gas streams out, of course, that means that if I, as a galaxy, was very keen to form a lot of stars around here, all the material would be gone. So you're basically removing material to make new stars. And at that point, what you have is a way for the black hole to affect the galaxy and to affect the growth of the galaxy. So that means that the black hole really can make a difference, right? It has all this energy and it can make a difference for the galaxy. So it would have a different future from if you just remove the black hole. I wonder what's, yeah, no, wait, I'll say something first. And so this is a very exciting discovery. The cool plot I showed you earlier is actually something that motivated research into it and people to understand this. And nowadays, if people run simulations of galaxy evolution, so they try to basically understand how the universe forms, so simulate the whole universe like that. What they generally do is they put in this effect of the black hole, right? They say like, oh, if you just take all that energy that comes out and we have it have an effect on the gas, how does that, the galaxy? So what I'm going to show you now is a film that shows the whole history of the universe. And I'm going to easy stuff like that. So this is from the illustrious TNG collaboration, which is an international collaboration. And they're one of the people that simulate the universe, good stuff. So I know this is old, illustrious, whatever, doesn't make a difference. Illustrious, not TNG. So what we're seeing here is like time since Big Bang, and we're now 1 billion years from Big Bang. So you can follow that along. So what we're seeing here is a slightly choppy way, is basically a massive galaxy forming. So what you see here, I want to kind of pause this video because then oh no, I can't pause this video. Right, so we're going to see a galaxy forming as a primer. So basically at the beginning, you see rather smooth structure. So that's kind of some material hanging about. And then what you see is a lot of collapse. So basically kind of gravity pulling everything together. And then fun things will happen. So basically all of this you see here is basically different material. It's just rotating for fun. So it's not actually rotating, basically the camera is rotating around. So what you see, we're now 1.1 billion years in, it's early in the universe. So what you see here is everything starting to fall together. So that's basically gravity pulling all the material together. It's a bit choppy, is it? But there you go. Oh, cool. Yeah, and then you might also see some things that look like mergers because the galaxy looked a bit messed up. It looks much better here. So, and all of those would be basically little galaxies. So you see a lot of them starting to form. And now you start to see these kind of little explosions around here. Poof, there's one going on here. And what those explosions are is the black hole. So here the simulation basically takes all the energy from the black hole growing, and it just basically calculates that it should heat the gas like this, it should push the gas out like this. And you start to see all this like massive explosion ripping all the gas out of the galaxies. And all of that would be something that, again, like stops star formation in those galaxies. We are now about halfway through the universe, more explosions happening. And this just carries on like this, and at some point it gets really boring. And then so by now, so basically this is halfway through the universe. At that point, the universe just becomes really, really boring because nothing happens anymore. And you're starting to see like a lot of the material is just kind of blown out of the galaxies entirely. And that in the simulation is what the black holes are doing, right? And that's what I described to you earlier, basically heating up material and pushing it outwards. And when I'm almost done, it's like, this is just boring now. We don't watch this anymore. It's just at some point it just gets tedious. Right, so hopefully I've kind of convinced you that the black holes do matter, but they can affect the galaxy. So I showed you a bit like how we might study, how black holes might feed, and then try to explain like what happens when you feed black holes. I then showed you simulations, which are lovely. One of the objections to the simulation, you might say, is like, well, what do physicists know? You know, they put in their physics, they might be wrong, and that's a sensible objection to theory, I guess, at least sometimes. So I also wanted to show you some actual evidence that this black hole affecting the galaxy actually happens, right? It's lovely that we can do the calculations, but do you see any evidence for that? And this is from this paper here from 2018, and I thought, no, it's this galaxy here. I forgot which galaxy this is, whatever. It's a galaxy with an accreting supermassive black hole. So what you see here is basically different evidence of actually material being ripped out of the galaxy by a black hole. And we see a few of those. So if we look at accreting black holes and we look at the very, very center, very, very close to the black hole, so a few light years or so, small distances, what we can see is basically signatures of gas near the black hole moving at about 30,000 kilometers per second. And that is fast. I mean, that is fast even for astronomers. So we have like 100 kilometers per second, yeah, whatever, that's kind of small fry, but we don't care about that. But that's 30,000 kilometers per second, and that's about 10% the speed of light. And we see that quite frequently. So near the black hole, we have clear evidence of gas moving that fast. And that tells us that the black hole is really pushing out this material. So that's 10% the speed of light. That's fast. It's really fast. So that's something we see very, very close to the black hole. We also see gas in galaxies on kind of larger scales. So that's kind of these kind of scales here, like about the same size as the galaxy. And again, here, what we can see is basically gas moving, and that's moving at about 1,000 kilometers per second. Now, these numbers all just start to be silly at some point, right? 1,000 kilometers per second, 30,000. But if you think about, so like the speed of light is kind of the limit how fast you can get. So 10% of that is really, really massive. 1,000 kilometers per second. If we want some reference, we can think like, well, is that fast enough for the gas to get out of the galaxy, right? If we shoot up rockets into space, we have to get to a certain speed for the rocket to escape, so it can escape velocity. So if we use that as a reference, that's about the escape velocity for a galaxy. So that means the gas is fast enough to just run away and never come back again, which is something we also saw in the simulation where the gas was just like floating about all over the place rather than coming back onto the galaxy. So from all of these observations, we know that the black holes can do amazing things, right? So we know that they can affect the galaxy. So if we go back to the picture of Markarian 231, which is a wonderful galaxy, what we can see here is we can see this black hole at the center. We can see this is accreting. We can see potential signatures of how this might have started because we can see the disruption here. This is also a galaxy in which we see these kind of outflows of gas moving out at these very, very high speeds. So here we can kind of see all the aspects of how the black hole is feeding and what it might be doing in a single object. This is my favorite galaxy, I think. And I don't even know why it is on the sky, so go me. Yeah, and so hopefully I've kind of painted you that picture of like how you feed the black holes and like what happens when you do that. Yeah, one more thing, chats. So I give this talk and then something in me at the end thinks like, oh, I'm really missing a major point. And the one more thing is chats. So I've talked a lot about the emission from black hole accretion, which can do wonderful things. The one thing I've ignored is actually in this wonderful cartoon image here, which you see this kind of jet coming out here. So what jets are is different. So I showed you these kind of fluffy outflows. So that's kind of just gas moving broadly. Whereas if we have jets, they're basically very thin. We call it collimated. They're more like a pencil than kind of just a wind coming out of the black hole. So jets like these ones here exist in some accreting supermassive black holes. They're pretty impressive. If we see jets, so jets, we generally see them in the radio. We would see something like that. So that's a galaxy. That's a galaxy. You see this galaxy here, all the little dust lanes here. So black hole would be at the center. And if we're talking about jets, we're basically talking about these structures here. So that's basically plasma coming out of it, and then you generally kind of, it basically crashes into the gas that is around it. So that's what jets are. So you always see two sets of them. Jets are interesting and complicated, and the physics is really hard. And the other thing to say to them is that, so I've described a lot of it about the emission from the accretion, but actually these jets can also have a massive impact, which I don't have time to explain you, but they also do things to the galaxy. So that's jets. Right, so coming towards the end, I'm playing again the evolution of the whole universe, so you can be reminded about what supermassive black holes do. Once the explosions go off, you know where they are, and hopefully I've convinced you that black holes matter for galaxy evolution. Thank you.
Thank you. Thank you for that. What questions do we have for Carolin?
I'm interested to know about how the supermassive black holes formed in the first place, how quickly, because I'm sure I've read an article recently where people get a bit twitchy. They were seeing them very early in the universe.
Yeah, no, that's an open issue, because you do see them like really early, and it's basically really hard to grow them fast, because there's basically a limit to how fast you can grow a black hole. So the accretion that I showed, it does emit the radiation, it also grows the black hole, but there's an upper limit to that. So it's hard to grow black holes fast. There's different ways to form black holes. Early one is basically like supernovae, like the same as supernovae. Basically, if you have explosions of stars at the end of their lifetime, if the star is massive enough, the center of it will collapse into a black hole. Right? So basically, massive star explodes, black hole left in the center. So you can do that. The problem with that is that the black holes are very small, as in like, I don't know, a few solar masses or so. That's a very small black hole. So again, you'd have to grow it super fast. There's other ways to form black holes early by basically just collapsing a gas cloud. That's a bit tricky, and some other more.
Or merger as well.
Yeah, you can merge them, but then you still need to grow them the same way. So it is a complicated thing, and we don't know the answer. But you need a seed black hole, and then you need to grow it really fast.
Yeah, because I'm hearing, I mean, some are thousands of millions of solar masses, aren't they? The biggest ones are 1,000 million.
Yeah, which is, I mean,
It's hard to imagine how that.
I mean, nowadays that's kind of pathetic, but like that early on, that's really high. And it's again this that they need to grow so fast. That's the problem. You have so little time. They have like a few 100 million years or so, which is really not a lot of time to grow them. So that's the main problem there. Need to grow fast. So I don't know the answer, and I don't think anyone does.
Do they think supermassive black holes cause galaxy formation?
not that they cause, but that they, so all the things I've shown here, so the base idea is basically the black hole basically kills the galaxy in a way. So that by heating the gas, by removing it, you basically stop star formation. And that solves a bunch of issue in understanding galaxy evolution. So they wouldn't cause it, but they basically cause a shutdown of star formation later on in the galaxy's life. So that is the main idea. I mean, a lot of this is kind of open research and you can find a lot of people to argue about it, but yeah.
So, do people understand why the supermassive black holes are at the center of the galaxy?
So you can do relatively basic simulations because they're individually quite massive particles. They basically just sink to the center.
Okay.
So they might not be at the very, very center, but they generally basically through interactions with the other material would travel towards, would migrate towards broadly the center of the galaxy.
Tony, do you have a question?
Yeah, I do. Can you hear me?
Yes, we can.
Yeah. You said during the talk that there's a relationship between the mass of the black hole and the mass of the galaxies generally. I can't remember what it was, but it's quite small. If the black hole is accreting, is it likely to change that relationship? I suppose it depends on the quantity and the rate at which it's accreting mass compared to the size of the galaxy, I suppose.
So the idea would be that they basically grow approximately at the same rate, so that it broadly stays on that relation, but they possibly kind of move up and down on that relation quite a bit. So broadly, the idea is that the black hole grows, the galaxy grows, and at some point you basically shut down the growth by removing all the gas. That's broadly the idea.
How does the galaxy grow? I mean, I know you could merge galaxies, but they're presumably two galaxies with the same ratio between the mass of the black hole and the mass of the galaxy. So it wouldn't change the ratio very much. So how would the galaxy grow?
So the galaxy grows generally by, so some of it is merging, some of it would be inflow of gas. So there is gas around it that can inflow, but mostly when people say growth, they also mean basically turning gas into stars, so growing the stars. Generally, when we say growth, we don't really care about the stars, we just want to have more stars. Yeah, it's mostly about
the stars. So when you talk about the mass of the galaxy, what you mean is the mass tied up in stars rather than including the mass of the gas and dust. Is that would that be? Yeah, okay. Just could I ask another question? You mentioned just now that the black hole kills star formation, and does that then affect the color of stars that we see near the center of the galaxy? Because there won't be, if star formation has been killed off, you won't have any young blue stars. They'll tend to be older, redder stars.
Yeah, that would be the case, because basically the idea would be that it stops the star formation, so no more new stars, so the galaxy would slowly go redder and redder because of that.
Yeah, okay.
So I think it was back in 2016 or so, the first gravitational waves were detected.
Yeah.
And I'm very curious of how do gravitational waves affect the feeding habits of black holes?
So I mean, if the black hole is just a black hole, it won't affect it at all, right? So you would get gravitational waves if you have mergers of supermassive black holes, which also need to happen, and we don't want to think about very much because there's a lot of complicated. So in that case, it would affect it more. But basically, gravitational waves would be emitted if you have mergers of supermassive black holes, which need to happen. What happens while the merger is taking place is very, very complicated, and we don't really understand. Because if it's feeding while it's merging, that's kind of a whole range of physics that is really unsolved. So it would possibly lose a bit of energy from it. But we don't see a lot of black holes, well, there's two of them close together. So we generally think that should happen, hopefully relatively quickly. So in that sense, for most of the black holes, it basically wouldn't have an effect, the gravitational waves.
Well, of course, I'll continue next year, sure.
Just to follow on from Tony's question, I guess when the black holes are feeding on gas and they're producing the radiation, and the radiation's then going on to blow the gas away, I'm guessing that kind of self-limits how big the black hole can get to some degree, and is that implicated in the ratio as well?
Yeah, exactly. So that's actually so the way the physics works out there is that basically, like once, like if the black hole actually manages to push away all the gases, of course also its own supply. So that would basically mean like galaxies stops forming stars, and that would broadly end black hole as well. So it's exactly this kind of self-regulation that would basically kind of set this ratio. Yeah, exactly. That's what would happen. So we don't know exactly how this works, right? There's a lot of this is open, but yes, this is how it would happen. It would shut off its own supply as well.
The other thing I was going to ask, dark matter, I understand it's 95% of gravitationally responsible matter in the universe. So when we get galaxy mergers, is that playing a role in these processes, dark matter? Does it get involved with black holes at all? I mean, is influenced by gravitation?
I mean, so for example, all of these simulations I've shown, it would have the dark matter in. So the dark matter affects the overall kinematics of the galaxies. The black hole itself, I don't think it would very much. The black hole is basically trapped in the galaxy, right? So
if 95% of gravitational mass is dark matter, and you're getting an accretion disk evolving matter, is there something analogous with dark matter as well in around the black hole?
A black hole, a dark matter accretion disk.
Yeah.
So people have asked me this before, and I was going like, I don't know if so some of it might accrete at some point, but I'm not sure like what the rate of that is compared to the accretion disk, to be perfectly honest.
Yeah, but obviously it's got no radiation, I suppose, the dark matter, so it does not play any role.
Yeah, it wouldn't.
Only gravitation.
Yeah, I don't know is my answer, unfortunately.
That's a good answer.
I'm trying to picture sort of a galaxy evolution, and we're used to the idea that interacting galaxies, the gravitational tidal effects of one galaxy to another can stimulate star formation.
Yeah.
And you're saying that can actually cause, or it can kickstart accretion to a black hole. But then if you're then seeing a galaxy which has increased star formation because it's been interacting with another galaxy, is that then part of the reason why it tends to ultimately end up as a boring elliptical galaxy, because then the black hole starts accreting and then it kills off the star formation? Is that part of the same continuum of processes?
Yeah, it is part of the same continuum. So this is kind of a theoretical model that astronomers are still trying to figure out the details, but there is this idea that to get to the boring elliptical galaxy, what you need to do is really kill star formation very, very efficiently, kind of basically no gas left behind to form new stars. So one of the idea is that the black hole has a role in that, so that initially you do see this increase in star formation. I mean, mergers are amazing at triggering star formation, but then basically that would be consumed, and then the effect of the black hole or other effects would basically shut it down to turn your elliptical galaxy into kind of a truly dead galaxy. Yeah, it will take a while. Yeah.
A quick follow-up to that question. If on those elliptical galaxies, surely once the stars that are in that galaxy die and become nebulae, would they not start the process again? And
Yeah, so the elliptical galaxies are also they're tricky, right? Because so this kind of goes beyond my simplified pictures for talks, because you can't say everything. So one of the problems with elliptical galaxies is that they actually have a lot of gas, because we're now in the wrong stage of the spill, but right at the very end, right, so you blow all this gas out, and you heat it up so it's hot and it's like around the galaxy, but it's still there. So one of the things that should be happening in elliptical galaxies is that the gas basically starts to like condense back onto the galaxy. So cool, it will, like, energy goes away, it will start to cool. So one of the things that should be happening in elliptical galaxies is that basically cold gas starts to trickle back in, forms a bit of stars. We don't generally see that, and we think that potentially the jets might play a role in that. So the jets which are left to the very end and basically ignored. One of the things they do is when there was earlier the, can I go back to the jets? Jets. So one of the things they could do, right, is that if the galaxy sits kind of in a pot of really hot gas, what those jets do is basically crashes into it and kind of heats it back up a bit. So if that gas that's like sitting around the galaxy is just starting to condense, it kind of like kicks it back up. So what it does is basically it keeps it in this mode where the gas is really hot, it's kind of far out of the galaxy, so you don't have new star formation. And the chat is what the chat seems to be what does that. So we see a lot of direct evidence of chats doing exactly that, keeping the galaxy nice and hot, free of cold gas, no star formation.
Thank you. I did have a little follow-up question as well. It was about quasars.
Yeah.
It was just to see if my understanding was correct. So, because I think they're sort of found in the early universe, aren't
Yeah.
they? So is it the fact that the galaxies, if you want to call them that, were so close to each other, so there was a lot of interaction going on between the galaxies that then produced these really, really massive black holes that then outshone? Is that the reason that there's so many of them are there in the early universe?
So quasars in general exist throughout history of the universe. We get
Right.
some, I mean, it depends like ways. So quasars generally some cutoff in like how bright they are, and so it's a bit of a murky like limit where you would call something a quasar. You still have quite kind of strong black hole accretion locally.
Mhm.
It generally all peaks at a certain time about halfway through the universe.
Right.
But one of the things is like everything peaks about halfway through the universe. About halfway through the universe, you know, everything is great, lots of things are happening, and then everything dies down. So it's generally, it's about kind of availability of gas. It is broadly that at some point you just start to use up gas to get the ejection of the gas. So it's the overall galaxy evolution that would affect both the black hole growth and galaxy growth. Yeah, we still get some nice quasars nowadays. Like 3C273 is basically in the local universe.
Ah,
So
okay.
it's actually 0.1 or so. It's like what 100 megaparsec away, so it's basically
Basically, and I just want to say thank you for a really interesting job. Thank you.
Any other questions in the room or from our Zoomers out there? I was actually going to ask, your 1% of galaxies are active effectively.
Yeah.
Is that 1% emerging, or actually do we see any active with no evidence of merging?
We see active with no evidence of merging, and that's kind of that's a fun problem. As in, so we see so. Okay, so first of all, the 1% is one of those like you give a talk, you simplify it somewhat, right? Because like activity is all relative. In a way, you could say the center of the Milky Way is active because like a tiny amount of gas is falling in. So that cutoff is generally something that you would see a significant like signature in the galaxy. Especially at the lower end, you see so it's 1% that are actively accreting approximately. At the lower end, you see a lot of them in like normal spiral galaxies. And the reason for that is most likely that if you have something that's accreting quite, you know, at a low level, it's okay to get a bit of gas to the center. That's fine, but it's relatively easy to do even in a stable galaxy. You can do simulations for that. At the high end, funnily enough, we also see galaxies with no signatures of interaction. We don't know if this is because there's another way to get gas into them. Another reason is that we might be really bad at identifying if galaxies have recently merged, especially if the merger happened a bit longer ago. So all these pretty pictures I showed are kind of, wow, this is really obvious. Once you wait 100 mega years, who knows, right? It's a lot harder to tell. So it's a very complicated problem. We see active galaxies without signatures of mergers. That's great. About 1% do have actively accreting black holes at some sensible level. Counting what fraction of galaxies have mergers is a whole other kind of work I don't want to do.
A few more PhDs in that one then.
No, my PhD students are using machine learning, which is kind of the newest thing. So that's where we kind of just outsource the problems to the computers now.
Says the rest of the world.
Okay, any last questions before we say our final thanks? Well, thank you very much, Carolin, for a wonderfully informative talk, and it complemented Dr. Becky's talk very well. So thank you for managing to dodge that bullet where I've organised two massive black hole talks very close to each other. So that's great. Thank you very much for coming down, and excellent talk. Thank you.